Yeah, thank you very much for inviting me, and thanks for coming to my talk. I'm speaking about quantum sensing with ultracold atoms. So sensors are everywhere. Animals use them to find their prey, your phones to show you where you are, and scientists to explore nature. And humans have built sensors for thousands of years. Think of Stonehenge, which is an astrolabium. Now imagine you live like 300 years ago, and the king orders you to build him the best clock in the world. Then you would most likely use a pendulum as the frequency reference for your clock. And such a pendulum is a man-made macroscopic object. You will never be able to build two pendula that have the same length and mass and tick at the same frequency. And therefore, one day, maybe the king will be late for his appointment with the queen, and then you're in trouble. But luckily, we are living in a quantum world, and the quantized energy levels of atoms provide us with ideal frequency references, namely the frequency of the electromagnetic radiation that is needed to drive transitions between the atom. And you can base lots of quantum sensors on such transitions, and they have the advantage that these atoms are given to us by nature. And as far as we know, an atom of a certain isotope is identical to another one of the same isotope. They're also very small, so you can build very small sensors. And you can engineer the quantum state of one atom on an ensemble of atoms such that it's very sensitive to the quantity that you want to measure, for example, the flow of time, and insensitive to other quantities, such as the magnetic field. And if you now want to build the best clock in the world, then you need to choose your atomic transition wisely. You should use one with a high transition frequency and a narrow line width. An optical transition with millihertz line width would be nice. You also want to get a lot of signal out of your sensor, so you should not only use one atom, but many atoms. However, these atoms, they may not touch each other, because if they would do this, the energy levels would be shifted around and your transition frequency changes. That means you need to use a gas of atoms. However, if you have a room temperature gas, such as the molecules in the air around you, these particles will move with hundreds of meters per second velocity. And then you will suffer from the Doppler effect. The transition will be frequency shifted. And you need to avoid this. That means you need to cool your atoms essentially to standstill. And to do this, you need a fridge, but not a normal fridge which you have at home or even a modern cryostat. That's just not cooling enough. You need a very special type of fridge, as shown on this photo. You see here a vacuum chamber, and on one side, we heat a sample of strontium atoms to 500 degrees Celsius, where these atoms sublimate, and then we have a hole, and atoms can escape the soil and form an atomic beam flying through this chamber with hundreds of meters per second velocity. And from the other side, we send a laser beam onto the atoms, targeting a broad line width atomic transition, so that we can scatter photons on these atoms. And each time an atom absorbs a photon, it will obtain the momentum of the photon and slow down by 1 centimeter per second. And after you have scattered tens of thousands of photons, your atoms have slowed down to meters per second velocity. And we push, with additional laser beams, we push the atoms to the center of our vacuum chamber and cool them even further. And if you look into the chamber, you see then this glowing fluorescence cloud of cold strontium atoms. They are millikelvin coated here. It's called a magneto-optical trap. Now we have further tricks to cool the atoms, and finally they are essentially standing still, and then we can capture them in a so-called magic wavelengths optical lattice, where they are resting then like eggs in an egg carton. Now they are ready to be interrogated. We build a laser that we shoot at our atoms, and if this laser has just the right frequency, the clock transition frequency, our atoms will get excited and we can easily detect this. And if the laser has a different frequency, then not all atoms will be excited, and we see this and can use this as our feedback signal to pull the laser back to the correct frequency. And that essentially is an optical clock, but it ticks at 460 terahertz. And not many people want a clock ticking at that frequency. So to overcome this, we purchase an optical frequency comp, which is a device which translates these high optical frequencies into microwave or radio frequency signals that we can actually use. And the best optical clocks built like this, they would go wrong by only 1 second over the lifetime of the universe. So what can you do with such precise clocks? You remember the movie Interstellar? Astronauts approach a black hole, and the ones which get closer age much slower because of gravitational time dilation. Now, we don't have a black hole close to Earth, so we can't experience this ourselves, but we have these super precise clocks, and they can detect the tiny gravitational time dilation of Earth's gravitational field. Now, our colleagues in Boulder, they have built 2 clocks and compared their frequency. Here you see the data. And then they used a forklift and lifted one of these clocks up by 30 centimeters and compared the frequency again. And you see the frequency is slightly different now between the 2 clocks. That's because of the gravitational redshift. And that was 10 years ago. Nowadays, the clocks are 10 times better. So we can see centimeter level height differences. What can you do with this? Imagine you live in a city near a volcano, and the volcano's magma chamber fills up, and then the volcano erupts. You would certainly like to know about this beforehand. You could build a network of clocks all across your country and connect these clocks through telecom fibers to compare their frequency very precisely. And if now the magma chamber fills up, the gravitational field above it will change a little bit, and that will make the clock above the magma chamber tick at a different frequency, and you can detect this. So you can use these clock networks to explore the underground. And we are scientists, so we can also explore cool scientific questions. For example, are the constants of nature truly constant? To explore this, we could build 2 clocks based on different isotopes or chemical elements. And then we compare their frequency today and in a year from now. And if the frequency ratio has changed, then possibly the fine structure constants or the electron to proton mass ratio have changed. Or you just made a mistake, which is probably more likely. We can also shoot clocks in space on satellites, and that could help improve satellite navigation, or we could measure the distance between these 2 satellites very, very precisely. This could give rise to infrasound gravitational wave detectors or test general relativity, help the searches for specific types of dark matter, or measure very precisely the mass distribution of Earth and see ice sheets disappearing, or help with building up a big radio telescope around Earth's radio dishes separated by millions of kilometers, which are synchronized through these precise clocks. Now, more practical applications. You know that GPS and Galileo, the satellite navigation systems which your phone use, they are based on timing signals sent to Earth from satellites. And yeah, we could improve these satellites perhaps with these optical clocks, but on this slide I want to focus on something else. Imagine you have a cargo vessel traveling through the ocean guided by these satellite navigation signals, and a pirate wants to have the cargo. Then the pirate could spoof these timing signals and guide the vessel into his welcoming arms. But if the captain would have an optical atomic clock on board, then it would be much, much harder for the pirate to correctly spoof these timing signals. Most likely, the captain would be just suspicious at these signals arriving there. They just don't match the local clock he has, and he would stay his course to the great disappointment of the pirate. And GPS is not only used for navigation, it's also used to synchronize our cell phone networks or power distribution grids. And if there would be a solar flare wiping out these satellites, our phone networks would desynchronize, costing us millions of euros per day. That we could synchronize these cell phone networks also through the telecom network, and these optical clocks could be very helpful as master clocks here. And once we have these super synchronized phone networks, then we can send timing signals from each cell phone tower, and cars could receive them and determine their location to better than 10 centimeters, which would be, of course, helpful for self-driving cars. And to bring these and other applications closer to society, we have created the quantum flagship consortium iqClock, Integrated Quantum Clock. It consists of 6 industry partners and 6 academic partners. And we have put ourselves 2 goals to get closer to our vision. So first, these optical clocks, they are really large and fragile. They fill a whole lab room, and you need 3 PhD students to maintain and operate them. Now we are building a small and robust clock made and tested by industry. And to give you a better impression of what's needed to build this compact clock, here again, the clock operation scheme with more detail. So first of all, we had this laser cooling stage on this blue laser cooling transition, which I showed you, which goes to the millikelvin range. Then we cool on another transition, which is much narrower, which helps us to go to the microkelvin regime. We can't just use this red laser cooling transition alone, because you can only scatter very few photons in the second transition. It would never be enough to slow the fast atoms coming out of the oven. But in combination, we get the best of both worlds. We can capture these super fast atoms and cool them to the microkelvin regime. Then we need the magic wavelengths lattice and the clock interrogation laser. And if the laser interrogates our atoms, it destroys the atomic ensemble, and we need to create a new ensemble, which takes a while. And lasers are nasty. This clock laser, it will not stay put on the atomic transition frequency if we don't do something, if there are no atoms present. So we intermittently lock our laser on a macroscopic reference and flywheel optical resonator that keeps the clock ticking while the atoms are not there. And finally, we need the optical frequency comp to do something useful with the clock. Now, lots of complicated modules. So here you see these modules in our lab, a laser system to cool strontium. Now, industry partner Optical takes essentially the same technology, but engineers it much nicer and puts it into rack-mounted laser systems. And NKT Photonics has made optical fibers which transmit at the same time blue and red light, simplifying the transmission of the laser light from these optical racks onto the vacuum chamber. Now, our vacuum chambers are way too big. Big is simple for us. It's cheap and easy to build, but for these clocks, you need really compact vacuum chambers, like the one here built by the University of Birmingham, and Teledyne E2V is now making a really small one for the final clock. And all the electronic needs to, of course, be integrated, done by Optical and Teledyne E2V. And Birmingham is now receiving all these modules, testing them and putting them into a final clock, which next year will be put into a test network center of British Telecom. Kronos will help us here to translate the clock output signals into the signals that Telecom needs to synchronize their network. And the second challenge we posed ourselves is to simplify the optical clock operation scheme. As you have seen, it's quite complicated, and we want for the first time to implement a simpler scheme and build a so-called Superradiant clock. But before I go there, let me zoom out a little bit and talk about our quantum sensing activities in Amsterdam in general. So one way of framing our research is to say that we want to overcome the problem that comes with pulsed measurements. So as I've told you, these atoms need to be first prepared with blue and red laser cooling and before they can be interrogated, and the interrogation destroys them. That means you can measure only sometimes. Now for a clock that might be kind of okay, but imagine you want to build another quantum sensor that should measure, say, acceleration or magnetic field. And these quantities really, they fluctuate all the time, like shown here. And since you have your atoms available only sometimes you will not record this whole time trajectory of your fluctuating quantity. You have to prepare your atoms, and then only you can measure. Then you have to prepare a new batch of atoms and you measure, and so on and so forth. Now, your measurement result is, of course, the quantity measured in these blue stretches, whereas if you average everything, it's of course different. So you made a mistake, an error, because of these pulsed measurements. So it would be really nice if we could measure continuously, and our new type of optical clocks can do this. And a key ingredient for that is that you need to have these ultra-cold atoms present all the time. So you can't just first prepare them and then use them for measurement. And this is something we have learned to do over the last years. So we now know how to continuously prepare a microkelvin cold strontium beam that is completely in the dark and suitable for these precision measurement applications. And we used this beam for two things. First of all, we want to make a continuous atom laser. And on our path towards this, we have created the first steady state Bose-Einstein condensate. And second, this beam is absolutely necessary to operate our new superradiant clocks. So, and I want to describe all of this to you now. And I will start with our goal to make a continuous atom laser. So what is a continuous atom laser? So a laser in general is a propagating wave that describes many particles. An electromagnetic wave in the case of an optical laser that describes lots of photons, and a quantum mechanical matter wave that propagates and describes the propagation of many atoms. It's just a coherent wave describing many propagating atoms. And both types of lasers are very good for precision measurement. Yeah, we can build laser interferometers to detect gravitational waves, for example. And we can also build atom interferometers. And the difference is that atoms, in contrast to photons, they have mass. So atom interferometers are very sensitive to gravity and gravity gradients and rotations and these things. So they're good for, say, inertial navigation purposes and also gravitational wave detection.
Sorry, there's a question.
Yes? Yeah, okay.
So, the question is regarding the pulsed measurement. Can you not minimize error from DC measurements by applying random pulse delays?
Yeah, sure, there are. Random alone wouldn't help. That would just randomize from where you pick up your error. It's true that you wouldn't then just get, I mean, if you Fourier transform your signal into frequency components, here we are really especially sensitive to noise at a certain frequency and its subharmonics. And that you could smear this out by randomizing, yeah? But you couldn't completely get around it. What people did already is they just duplicate the machine. They build two machines and alternate between the two. That would work too. But it's twice the effort, yeah. Okay, so people have created atoms or lasers already, but they are pulsed atom lasers. What do you need to do? You again need to cool, say, strontium atoms. In the first experiments was always rubidium atoms. And actually laser cooling alone is not quite enough. You need to cool further with evaporative cooling. Why is this? Even if you have atoms that are completely standing still, if you have these laser cooling photons around, these atoms could absorb a photon from a laser cooling photon, and that would accelerate the atom to about 1 centimeter per second velocity. The atom would be a thermal atom again, and that wouldn't do. You need atoms in the quantum mechanical ground state of motion of your trap, for example. So evaporative cooling can bring you there and create what's called a Bose-Einstein condensate. It's just like many atoms at the same time occupy the harmonic oscillator ground state of the trap in which you confine your atoms. So this is kind of like an atom laser, but it's stationary. In an optical laser, that would correspond to the optical field in a lasing cavity. Now, to make an atom laser, you just punch a hole into your container and atoms trickle out by gravity And that, of course, depletes your Bose-Einstein condensate. If you have a decent flux in your atom laser, after 100 milliseconds, you will have no atoms left anymore. And then you have to cool a new ensemble of atoms and make a new BEC. And that makes your atom lasers pretty useless because there's no phase coherence between the individual pulses. So it has been clear since a long time that for a continuous atom laser, you have to execute all these cooling stages, not one after the other in time, but one after the other in space. And there have been quite a few attempts to make this work, but always using rubidium. By the way, here on this picture, you see how the last stage could look like, where you evaporate your atoms while they are drifting down a guide, which is shown in red. They evaporate till they are cold enough to populate the harmonic oscillator ground state mode of your guide. Good, and with rubidium, it just hasn't been possible because rubidium has relatively poor laser cooling performance, and the Bose-Einstein condensate is just incompatible with the laser cooling atoms. Now, the speciality of my group is to work with strontium. And strontium is an alkaline earth element, rubidium is an alkali element, so we have two valence electrons and much richer optical transitions. We do also have a broad line-width transition, the blue one here, which we absolutely need to cool the fast atoms coming from an oven. But we have also a kilohertz line-width transition to cool to the microkelvin regime. Something like this is just not available in alkalis. Also, we found a trick to make our atoms transparent so that they just don't absorb any light anymore in this narrow red laser cooling transition. And now we want to use this to make an atom laser. And the first step to do this is, of course, to make a Bose-Einstein condensate that exists forever. That has never been done. Usually they always decay by loss processes over the time of a few seconds. And to do this, we have created, there's one more problem which we need to solve. So we can make our atoms transparent against these red laser cooling photons, but not against the blue ones, which we need to slow the fast atoms coming from the oven. So to get around this problem, we built a new machine, which is shown here on this picture, where we execute all these laser cooling stages one after the other in space. Yeah. So the atomic beam drifts through the two chamber. First, we have blue laser cooling stages and red laser cooling stages. And then we were recently able to make a steady state BEC. And I want just to explain this a little bit more in detail by zooming in on the last step of the machine, which is happening down here in this vacuum chamber. So here we have this small fluorescence cloud of atoms, a laser-cooled cloud of atoms at the microkelvin cold, magneto-optical trap. And it is exposed, of course, to this laser cooling photon light, and it needs to be relatively bright. We can't make a steady-state BEC or atom lasers there, so we decided to move our atoms in the final stage a few centimeters to the side where we can make the system really dark. We push it into a so-called dipole guide. This is just an infrared laser beam. It's attractive for the atoms, and the atoms just follow the, it's an attractive tube for them. They just flow along this tube, and then at the end, we slow them down again and accumulate them in a trapping potential, so-called cross-dipole trap. And if you look at the system, it looks like this. We accumulate our atoms here, and just here in the middle, we will then, where the density is the highest, we will use our projection trick and make the atoms transparent against the laser cooling light. Now we have to look if we perhaps did get a Bose-Einstein condensate there, and if it lives forever. So first, how do we detect a Bose-Einstein condensate? I'll show you a few images how one can do it if one loads the trap and then performs evaporative cooling, so to get it really cold to know for sure that there's a BEC there. Now, usually the cloud is extremely small and you can't detect the BEC. So what you do is you suddenly switch your trap off, then the atoms fly in the direction in which they just had at the moment you switch the trap off. And if you have a thermal cloud of atoms, the atoms just spray out in any which direction, and they form this round isotropic blob of atoms on your, this is the density profiles of the cloud, which we record by absorption imaging on our cameras. But if you made a BEC, it expands very differently. A BEC, it has interaction energy between the atoms, and these atoms repulse each other. Now, initially, we confine our atomic cloud quite strongly in the vertical direction, which is like we squish the BEC in the vertical direction, giving it a kind of pancake shape. And now, when you switch the trap off, this mean field energy, this interaction energy between the atoms that is released during the flight, and it's released mainly in the direction in which you initially squished the gas. And that means that the BEC, which initially looked like a pancake after this time of flight expansion, looks like a cylinder, which you look at from the side. This gives you this elliptical feature. So in my images, if you see something elliptical, that means there's a BEC there. Now, this BEC, which we have made here, that will live only a few seconds because of chemistry going on, molecule curation, all kinds of nasty effects. Now, let's use our continuous machine. We switch it on and charge our trap for a while. And then, of course, for detection, we need to suddenly switch it off, let our gas cloud expand, and we get then this blob of atoms. Here, the atoms from the guide, they give rise to this feature. Here, the atoms in the center, that's the ones which we want to see, they give rise to this feature here. And here are atoms that just flow from the guide into the final dipole trap. Now, there's nothing elliptical on this picture, so there's certainly no BEC. Now, let's do the same experiment over and over again with one difference, that we load each time a little bit longer in our dipole trick. We accumulate more and more atoms, 2 seconds, 2.5, and that, you see, if we wait longer than 3.5 seconds, suddenly you see this elliptical feature appearing. And that's indicative of a Bose-Einstein condensate. And you can also see that this Bose-Einstein condensate that just lives on and on and on for as long as you want. It's a system in flow equilibrium. Atoms are destroyed all the time by chemistry and all kinds of nasty effects, but we push new atoms into the system, keeping the Bose-Einstein condensate alive for minutes, for as long as we want. This is, by the way, in itself an interesting system that we want to explore, driven dissipative Bose-Einstein condensate or quantum gas. Now we want to further prove that we have a BEC, and how do you do this? You fit theory to it. And if we take a theory model which only includes thermal atoms, it can very well describe this cloud before BEC is created, but afterwards, no. It doesn't match it. There's this elliptical remainder. That's a BEC. And if we, of course, add what's needed to fit a BEC to our fit, it fits perfectly. So we are quite convinced that this is a BEC, which we see here. Good. And now this is the first, really a very important step towards a continuous atom laser. Now we have to just learn how to punch a hole into our container and extract this atom laser. Or there are also different ways of doing it. But, yeah. Now, on our way to create this steady state BEC, we created this microkelvin called beam of atoms in the dark, and that is also useful to create these super clocks. Now we are back at our quantum flagship project, our second challenge to make the superradiant clock. So what do we want to change? In normal clocks, these atoms are only there intermittently. We now have atoms available all the time. And that means we can also get rid of this complicated flywheel optical resonator, which is, for example, very difficult to operate on a moving vehicle. And you want clocks on moving vehicles, like the cargo ship, which I've shown you.
Yeah, there's a question about the previous thing, about the simulation or the theory. And the question is, does it need a simulation? And if yes, are there quantum complexity blowups for simulating this, this fit?
So this theory is very simple. There's no simulation involved. We just fit Gaussians for the thermal cloud and the so-called Thomas Fermi profile here. However, there are other properties like how the BEC is created and the ratio of the atom number in the BEC in the thermal cloud, for which we tried simple steady state equilibrium theories, and they just didn't match. And then Jeremy Na, who is a postdoc with us and with Kalyan's group and here, so he came up with a theory model with a numerical, it's a differential equation which he would have been able then to fit to our data. And what he found out is that our thermal gas is clearly not in equilibrium. It's because we constantly feed hot atoms into the high thermal tail of our gas cloud. So that was interesting. Now, complexity problems. So what I do know is that these driven dissipative quantum many-body systems, they can show quantum phases that equilibrium systems can't have. And they're really fancy quantum phases out there. And we can hopefully push our machine into a regime where we can explore these phases. Now, if there are computational problems with these phases, I do not know. Yeah, that's as much as I can tell you about this topic.
Thanks.
Good. So now we want to build this different clock, yeah? The Superradiant clock. And one way of seeing what or describing what we want to do here is also the following. In a normal clock, you passively interrogate the atoms. You first prepare an ensemble of ultracold atoms, and then you send a laser beam onto the atoms, and the atoms react and go to the excited state if the frequency is correct, or they don't do it, and you detect this. This is called a passive clock because the atoms are passively involved in it. We send the laser onto the atoms. Now, a superradiant clock is an active clock where we entice the atoms to directly send us photons on the clock transition. Yeah, and that works by sending a continuous stream of microkelvin cold strontium atoms, all excited to the upper clock state through a cavity. That doesn't have to be a particularly good cavity, not like the one which we usually use. And then we use a trick to every atom emit one photon on the clock transition into the cavity mode, and out comes a laser beam on the clock transition directly, yeah, actively. So yeah, we think we can do this because we have, yeah, one component is that we have figured out how to make this continuous beam of atoms. Now, what's the difficulty here? This transition is only a millihertz wide, which means that the optically excited state lives for minutes. So if you have like 100,000 strontium atoms, all excited to the upper clock state, you would have to wait for minutes for each atom to emit a photon. And then these photons are emitted into 4 pi into any direction. And that's pretty useless. You can't really do something with these photons. And the trick now is to entice these atoms to emit all their photons into the same direction, and also to emit many more photons than given by just the lifetime of the excited state. And how do you do this? You do this by superradiance. And then classical analogon for this are phased array antennas. So imagine you have n antennas all emitting at the same frequency, but with random phases. That's what I symbolize here with these arrows. Then the total output power of the system would be just n times the power of an individual antenna. And that's not a very good scaling. And it goes into all directions. That's a problem which we have. But if you would make it such that all these phases of all these antennas are synchronized with each other, then you could make it such that all the electromagnetic radiation in one direction constructively interferes and in all other directions destructively interferes. And then in this one direction, you get n times the electric field amplitude of a single antenna. And the power scales with electric field amplitude squared. So you get power scaling with n squared the number of emitters. And that's very good. So we get, if we synchronize them correctly, we get the scaling. And how do we synchronize? We again put this cavity around these atoms. And now what happens is that first you start with all atoms in the excited state, and then once randomly, by spontaneous emission, a photon will be emitted into this cavity mode. And then the universe and us, we just can't know which atom emitted this photon. And the ensemble of atoms goes into a quantum mechanical superposition state of first atom emitted a photon and all the others not, plus second emitted a photon and all the others not. That's a so-called Dicke state. And it has the property of radiating more photons into this cavity. And then you get more and more complicated superposition states, and it radiates faster and faster. There's a real avalanche which is happening then. And that was shown in pulsed mode by James Thomson's group at Schiller. So they put strontium atoms in the optically excited state into such a cavity, and then out come these pulses of light on the clock transition. And yeah, okay. And that's nice, but for a clock, you need to have it working continuously. And that's what we want to do in our project. And one more remark, the system looks an awful lot like a laser, and indeed it is a laser, but it's absolutely not a normal laser. Let's make this comparison. In a standard laser, you also have an ensemble of atoms in an optically excited state inside a cavity. And now you use stimulated emission to emit photons. So you need a huge electromagnetic field in your cavity, which means you need a very good cavity with a narrow line width, much narrower than the transition line width of your atoms. Now, if the cavity length changes by Brownian motion or by sound waves or something like this, then the frequency of the outgoing light will change, because the frequency is determined by the cavity mode, by the length of the cavity. And that's very bad. We have built a classical clock here, not a quantum clock. And a superradiant clock laser is very different. The cavity is only there to synchronize this ensemble. We don't need a large electromagnetic field, which means the cavity mode can be much larger than the atomic line widths, and it still will work. And that means if the cavity now vibrates in its length, it doesn't really matter. The phase stays stable. It's given by the atoms. And so our iqClock project started in October 2018, and our Copenhagen partners, they have shown now in the kilohertz transition pulsed superradiants and made a lot of theory. We have designed actually 3 different types of machines, which we want to show this in different versions. First on a kilohertz transition, simplified, and then on a millihertz transition. Here's one example of this machine, and we are in the middle of our probably closing in on the end of the construction of our machine. And you will see this in the virtual video lab tour, which I'll have at the end of this talk. Yes, so this is what I wanted to tell you about our quantum sensing activities. This is not all what we are doing. We also have quantum simulation computing activities, an NWO program on rubidium strontium molecules, and also with René Geretsmann ytterbium-1. And then we have a project together with QSoft and the Quantum Software Consortium, and now also because of the Quantum Delta NL Start Impulse with Theo Eindhoven. And this is the first project we will show you in the lab tour, because it's related to QSoft also, but also because one still sees the most. In the other projects, there's not so much to be seen. And because the atom laser is all hidden, and the superradiant clock project is not yet built. So we will show you also this project, and I want to say a few words on it. How do we want to use individual strontium atoms to make quantum simulations and computations? And what's the link to the rest of my talk? Now, the link is that qubits are clocks in a certain way. Yeah, there are also 2-level systems. And if you want to make qubits with ultracold atoms, people made 2 choices so far. Either they use the simple alkali atoms, where you have 1 valence electron, and there you use the 2 hyperfine levels as your qubit 1 and 0 states. Or as us, you use alkaline earth atoms, and there you also have hyperfine levels for qubits if you want, or even qubits. And you also have the clock transition as a nice qubit transition. So what we have done so far is we have made an array of teeny tiny so-called optical dipole traps, optical tweezers, and we can load strontium atoms into these arrays. Here you see the fluorescence of strontium atoms in an array of these tweezers. And single qubit operations you can make on these atoms by just shining laser beams on them and exciting them on the clock transition, imprint phases, whatever you want. The challenge is always the 2-qubit interactions, and there we will use Rydberg interactions. So yeah, just how does this work roughly? So imagine you have 2 atoms that neighbor each other, and you want to make a 2-qubit gate. And let's say blue here is 0 and 1 is red. So you send a pulse of light onto your first atom, if this first atom is in 1, then it will be excited into a so-called Rydberg state. That means it's going into a state where the electron is far, far away from the nucleus. It's a very fluffy state. And if your other atom, and your other atom could also be driven into such a Rydberg state, but both atoms at the same time can't, not easily at least, because if both are in this Rydberg state, they will strongly interact with each other by van der Waals interaction, for example. Just because they are so huge and fluffy, and the electron shells of these two atoms, they influence each other. So if the first atom was in the 1 state and got into this Rydberg state, then the second atom's Rydberg state will be shifted out of resonant. And if you put a second laser beam onto it, it will not be driven up. So you can make a phase gate like this, independence of the, if the first atom was in 0 or 1, you will or will not drive the second transition in the second atom. And good. And yes, so here are all the people which are involved in all this research, and we all wish QSoft happy birthday. And some of the team members have now even prepared a video recording to welcome you in their labs. But perhaps you have questions first on my talk.
Julian, would you like to ask your question?
Yes, I can do this. Hey, Florian, nice to talk to you again. I was interested in, you were talking about using optical clocks as quantum gravity sensors. And I think currently all systems being explored for as gravity sensors are based on atom interferometry. And I was interested in how far your system based on clocks has a competitive edge towards these systems, or what would be the unique selling point of using optical clocks?
Yeah, you could use it. I mean, I'm not doing this myself, but other people do this. So they have established this network of clocks from Paris to PTB in Braunschweig and London, and connect all these super precise clocks. They can use it for geodesy. They know the absolute potential difference between these different locations in Europe.
Okay, so the use case is not to drive them around and have a mobile system which can be positioned anywhere you like, but they will be on fixed space measure. Okay, clear. Okay. Yeah, thank you, Florian.
Don, you also had a remark about the OT. Would you like to discuss that now?
Yeah, sure. I wasn't actually going to ask wasn't going to make the dumb remark, but now I'm going to make the dumb remark anyway, because there were two really funny things I enjoyed from this talk, apart from the immense technical achievement that this is. So the first remark is, I thought that emitting into 4 pi was the coolest jargon for all directions that I've ever learned in my life. And I think, computing on fluffy atoms gives it a very, very close second. So those are cute things from your talk. But I had sort of a more serious question and or remark, which is, I don't know if you've talked to quantum cryptographers much about this, but when you started talking about having a superposition of atoms in states where, maybe it's atom 1 that emitted a photon, but we don't know. Maybe it's atom 2 that emitted a photon, but we don't know. That smells just like oblivious transfer in the crypto world. So I'm wondering if, maybe there are thoughts about developing a mechanical device for something like oblivious transfer. Now,
I don't know oblivious transfer, so.
Yeah, well, you defined it. That's literally almost the definition. Like, I send you a message, I don't know if you received it or not. Or a slightly alternative one is I send you 2 messages, you get one or you get the other, but I don't know which of those 2 messages you got. So it has exactly this flavor of a photon got emitted, but we don't know which source it came from. Maybe it came from the first, maybe it came from the second. And once you get that, you have kind of an imbalance in knowledge between 2 parties, like the source and the destination. So that imbalance in knowledge It means you can start hiding things. You can start, making people behave because they can't sort of change, after the fact, the kind of things that they declared in the beginning, because they don't know where they're getting tested. They don't know what has been looked at in their system. So they kind of have to behave, very, very well. Otherwise, they're going to get caught in cheating. So it's very, very useful for quantum crypto. The downside is that, for a couple decades, we've known that commitment and, oblivious transfer maybe is theoretically impossible, because if you have a quantum computer, you can kind of change the game a little bit. But until people have powerful quantum computers, you may not be able to cheat these systems. So even some of the theory that says you can't do it may not really be technically applicable. So that's a very long-winded comment then to you, because it sounds like you haven't. But that sounds like a very interesting direction maybe to follow, to talk to some crypto people and to say, hey, maybe we have a new technical implementation of oblivious transfer using actual atoms and photons.
Okay, yeah. I mean, you can, I don't know if you need access to these individual atoms, but you could put a tweezer array of strontium atoms inside a cavity. So you get these photons out. You don't know which one emitted, but you could afterwards look at it by projecting the state. Right. I mean, we can play around with these ideas. Probably there's a lot more possible.
Yeah, no, I mean, it could be very offhand, but it just really smelled like a potential for something. So cool.
Interesting.
Thanks.
Then, Florian, maybe then it's now a good time to first move to the videos, and then afterwards there will be maybe some more time, but for people that have to leave at the right time, and then switching the screen sharing.
No, I need to screen share in the special mode, which enables videos, which means I can't see you guys. So you see it, yes?
Yes.
Oh, hi. Welcome to the Laser Labs here at University of Amsterdam. I'm Alex Schreck, a PhD student with Florian Schreck, and I'll be showing you around this lab today, or at least the beginning of the lab, and then you'll see some more of the other experiments from other people. But so, for my experiment, I work with optical tweezers, in which I trap single atoms of strontium inside very tightly focused laser beams that we create by sending the off-resonant lasers through a microscope objective and focus the lasers down to a sub-micron spot size that then allows for us to prepare single atoms nicely. So then to do this process, I'll kind of go through some of the things that Florian has already probably mentioned to you. And that will include first the oven, in which we take a rock of strontium. We heat this rock of strontium up to create a gas of hot strontium atoms. These atoms are then collimated into a hot atomic beam traveling at about 500 meters per second as it goes through this, these tubes here. And then it enters the Zeeman slower, in which it undergoes laser cooling with the laser beam propagating this way and a magnetic field that helps to keep this laser beam resonant with the atoms as they get cooled down to approximately 30 meters per second in this main science chamber. We then use additional laser cooling techniques known as magneto-optical traps to then catch the atoms and make a cold cloud that we then move into the focus of this microscope objective and then catch atoms inside these tightly focused optical dipole traps known as optical tweezers. There's some other things here, which is a versatility of our machine, but we'll ignore this for now. But to do this process that I'm just explaining already, you need a number of different lasers, a lot of optics, and we then have all of these lasers and these optics on the other optical table that I'll show you in 1 second. But for now, I also wanted to show you then that we sit here to control the experiment. We have different monitor computers for monitoring the magnetic fields and the temperature of the oven and other things like this, and then our control computers and imaging processing that goes on to actually determine whether we have 1 or 2 atoms inside of the tweezers, or 1 or 0 atoms. Sorry. And then to do this, we also need a number of electronics. We need a very high vacuum. We need different ion pumps for getting very nice vacuum. We have all these electronics for controlling the different laser frequencies, and for the frequencies of the lasers, for controlling the currents and the temperatures of the different lasers. And and then additionally, we need all of these additional optics for basically manipulating the frequency of different lasers using acoustic optic modulators, and then this whole mess of fibers that allows for us, of optical fibers that allows for us to bring the laser light to the proper place on the experiment. You can also see these boxes along with different external cavity lasers that we use for different applications, such as repumping the atoms or manipulating their internal state, which includes then allowing for us to do things like coupling the neighboring tweezers, which are farly separated by Rydberg interactions, which then happens from exciting the atom to a very high electronic state. So I think that'll end things for me, and I'll pass you over now to Benjamin that'll explain the atom laser experiment for you. Thanks. Have a good day.
Oh, hello. Well, welcome to the Atom Laser Lab. My name is Benjamin, and today I'm going to show you a bit around, show you our experiments, right? So what we're doing in this experiment is we're doing an atom laser, but we're trying to have a continuous wave atom laser. How do you make an atom laser? Is typically you make a Bose-Einstein condensate, so it's a quantum state of matter. And we're using strontium atom for that. And once you have your Bose-Einstein condensate in a trap, what you typically do would be to outcouple it into a stream of atoms falling from this Bose-Einstein condensate. And this stream of atoms is just like the atom laser beam, just like a photon laser, where it's a stream of photons that is directed and that we can use later for doing atom interferometry measurements and other kind of fundamental science, but also for society application such as mapping underground resources, for example. You can do that with an atom laser. You can measure acceleration, so it can be useful to unbob that in a boat, for example, or you can map resources on the ground because atoms feel gravity, so you can measure variation of gravity without even probing the floor, just by putting your atom laser above it. So one problem with atom lasers is that once you have your Bose-Einstein condensate, you make it leak, the atom leaks, and at one point there's no atom in the Bose-Einstein condensate anymore, and that's the end of your pulse of your laser. So, and that's a problem because that limits a lot the precision that you can achieve, that limits the usability of atom lasers. So what we're trying to do is to make a continuous atom laser. For that, we need to refill fresh atoms into the Bose-Einstein condensate while it's outcoupling. And we use the same technique as other experiment that you will see or have seen. It's we start with a chunk of strontium atoms, metallic strontium, that we heat it up to 500 degrees Celsius. So we start with hundreds of Kelvin hot atoms. It makes a stream of hot atoms as a gas jet, and we're going to go across the chamber through different chamber and different cooling stage. These cooling stages are made by laser cooling, and we just funnel the atoms from one place to another while keeping the flux as high as possible, so not losing atoms, but trying to make it denser and trying especially to make it colder. So we pass from hundreds of Kelvin to millikelvin in this chamber, to microkelvin at the bottom chamber, and in the end we refill the Bose-Einstein condensate, which would be at a temperature equivalent to a few nanokelvins. And it can be quite challenging. So for example, from the top chamber to the bottom chamber, there's about 40 centimeters, and the atoms are just falling because of gravity, and we have to catch them back with a very weak laser cooling transition. It's weak because you can achieve the best temperature, but it's weak so you can only achieve deceleration on the order of 16 G. So you have to laser cool a lot and for a long distance and efficiently to catch as many atoms as possible. And since last year, what we succeeded in doing in this experiment is to, for the first time, funnel the atoms continuously to refill continuously a Bose-Einstein condensate, such as it never stops. Right now, the Bose-Einstein condensate, it doesn't explode. What it does is that it creates molecules because it's too dense, and that's our losses. But we hope that in the future we're gonna just find a way to outcouple atom of this Bose-Einstein state like other atom lasers, but this time the beam will never stop because we have a full refilling mechanism. It stops only when there's no more metallic strontium in the oven, and that's in 5 years or something. So that's a bit the status of our experiment. The technology here is similar to lots of cold atom experiments. So you have a vacuum chamber where you have ultra high vacuum, about 10 to the minus 11 millibar, and you have hot strontium, lots of laser cooling. So you need optics, you need your lasers. They're mostly on the full table contains what you need for the experiments. So lasers, lots of optics to shift the frequency and collimate your laser beam and send it into optical fibers that you will send on the experiment in the end. And of course some electronics that you use to drive the lasers, control frequencies, and all this electronics will be controlled with our computer system. And in the end, when everything is built and is ready, our PhD students, for example, will be on this computer and just clicking button, producing a continuous atom laser and using it for precision measurement. So that's about it. Thank you for having listening, and I leave the next experiment.
Hello. Welcome to the iqClock lab. Here we're aiming to make a Superradiant clock, and I'll show you how we plan to do it. So let's start from here. This is our vacuum chamber, and is actually the final step. So we are just building now. And yeah, the light is finally gonna come like here. So I've started from the end, but let's go a little bit before. So to build our Superradiant clock, we need to manipulate atoms, and in particular we are working with strontium, so we need some lights. And in order to have them, we built several laser systems. So we have a lot of this kind of lasers that are slave laser. So basically, we take light from another lab, and we inject this light into the slave laser, and then the slave laser is giving us the frequency we want. So once we have the light of the right frequency we need, we can redistribute it in order to have all the different lights, different beams that we need. And here you can have an idea of the scheme we have to think about, because there are different cooling stages, different lights we may need, and these are all the beams that finally we end up having. And that's why we don't simply need 2 boards, but an entire cabinet of lights. So you can see here, they are our optical breadboards. Here was a blue one. Okay. All these lights are, of course, electronically controlled. So, just on the upper part of this cabinet, we have the electronics for the lasers, the controller, and temperature controller. And to modulate the different frequencies, to choose the different frequencies, we need optical modulators. And they also require the electronics, so we have an electronic cabinet full of everything that we need to power our racks and make our ARM working. Okay, and now let's go to the real boss of the experiment, the person that has designed everything, that will show us how something goes from an idea to a vacuum chamber. Okay, here we have Dr. Schindler.
So we start off with an oven here with strontium pieces, which we heat to about 650 degrees. And that ejects atoms out through a nozzle up through here, we've got some heat shields to prevent the oven from radiating too much power. And then we've got some transverse cooling stages. Then we go up through a cavity, which is where all the action happens. So here we've got a cavity. This whole thing's chopped in half at the moment. And up here, all of this is vibration isolation stacks. So this is to try to get rid of all the acoustic noise.
As I told you, we are still building our experiment, so we don't have the oven yet, but I can show you the parts that we have, so the nozzle. Okay, here is the oven nozzle that Camila assembled, the person that is doing the video. And you can see all the hundreds of microtubes she has to put inside. It took an entire morning, and yeah, she did almost one by one. A funny job. So from the oven to the nozzle, and then to the cavity. Once it's going to be finished, of course we cannot stand the whole day like controlling everything and so on and so on. That's why we have a complex system, and yeah, so you can see here